The first law of thermodynamics tells us that energy is conserved, or in the context of our calorimetry experiments, when a hot object comes in contact with a cold object, heat lost from the hot object must be gained by the cold object. You'll notice the plus sign, then the calorimeter constant times the change in temperature of the cold object. Recall, the hot object is losing heat to the cold object, and some of that heat is also transferred to the calorimeter itself. I explained the calorimeter constant and how to get the calorimeter constant in another video. Our calorimeter constant is small because styrofoam is a good insulator and doesn't absorb much heat. Thus, the calorimeter constant can be ignored, which I've shown in my earlier calorimetry experiment videos. I'll ignore the calorimeter constant in this video. Check with your instructor for specific instructions. Here's the equation. On the left side of the equal sign, I have the heat equation for the hot object. Heat is equal to negative mass of the hot object times the specific heat for the hot object times the change in temperature of the hot object. The negative here is to represent that the hot object is losing heat. The hot object will decrease in temperature. The change in temperature will be negative. Thus, the negative signs will cancel in the end. On the right side of the equal sign, I have the cold object. The mass of the cold object times the specific heat of the cold object times the change in temperature of the cold object. In this experiment, the metal will be submerged in boiling water and mixed with cold water at room temperature. The metal will be the hot object and water will be the cold object. I strongly recommend setting up the equation first. I'm looking for the specific heat of the metal, so I'll divide both sides by negative mass of the metal, or hot object, times the change in temperature for the metal, or the hot object. And I'll include the negative sign as well. This gives us the equation to find the specific heat of the metal. I'll need the mass of the cold water, the specific heat of the cold water, and the initial and final temperatures, along with the mass of the metal and its initial and final temperatures. Here's a list of specific heats of some metals. Your instructor will provide you with your lab's list. Notice, metals like zinc and copper have the same specific heat to two significant figures. So if we identify these metals, we'll have to differentiate them based on other properties, like color. Aluminum, brass, and stainless steel, which is primarily iron, are other metals used in our lab. Now, let's get to the lab. I'll run 3 samples and show you the calculations for each. The first sample are metal pellets. The second and third samples are cylindrical shaped metals with a string attached so we can handle them. The metal pellets have a mass of 30.386 grams. The smaller cylinder has a mass of 27.240 grams, and the larger cylinder metal has a mass of 81.828 grams. You'll also notice I've transferred all the metals into their own test tube. Let's start with the metal pellets. I'll set up a boiling water bath and transfer the test tube into the boiling water bath. It is important that the metal inside the test tube is submerged in the hot water bath. I'll let the metal sit in the hot water bath for about 5 minutes. This allows the metal to come into thermal equilibrium with the hot water bath. Thus, we can safely assume that the temperature of the metal is the same as the temperature of the hot water, 100 degrees Celsius in this case. I'll transfer exactly 50.0 milliliters of water into the styrofoam calorimeter, which I have shown and explained in earlier videos. The initial temperature of the water in the calorimeter is 22.9 degrees Celsius. After about 5 minutes, I'll use a test tube holder to handle the hot test tube, then quickly transfer the metal pellets into the calorimeter. I'll swirl the calorimeter cups and read the final temperature, 27.0 degrees Celsius here. So let's put the data together for the metal pellets, the first metal that we studied. For the mass of water, recall in the calorimeter I added 50.0 milliliters of water, so I can safely assume a density of 1 gram per milliliter, so we'll call that 50.0 grams of water. This is times the specific heat of water, so that's known, 4.18 joules per gram per degree Celsius. And for the change in temperature, I have a final temperature of 27.0 degrees Celsius minus the initial temperature of 22.9 degrees Celsius. This is divided by the negative sign. I have the mass of the metal. So for the first trial, those pellets were 30.386 grams to the nearest milligram. And the change in temperature for the metal, the initial temperature is 100.0 Celsius, so the boiling point of water, and the final temperature of the mixture, 27.0 Celsius. So these final temperatures, of course, are the same. They come into equilibrium. So the change in temperature here, this is going to be 4.1 degrees Celsius. In the denominator, this change in temperature is a negative 73.0 Celsius. Those negative signs will cancel. And so we'll answer this specific heat to 2 decimal places. And to 2 decimal places, we get 0.39 joules per gram per degree Celsius. So this looks a lot like zinc based on the color. I'll follow the same steps for the second and third metals. These metals are designed so that a string can be attached to them. After about 5 minutes, I can simply transfer the metal to the calorimeter by using the string. Here's my second trial. For the second trial, again, I'm using 50 milliliters of water, so this stays the same. We'll call that 50.0 grams. The final temperature is 26.6 Celsius. The initial temperature, 22.8, very similar to what we had in the first trial. That cylinder had a mass of 27.240 grams. And for the cylinder, the smaller cylinder metal, the final temperature 26.6, and the initial temperature again right at 100.0 degrees Celsius. The change in temperature here, 3.8 degrees Celsius. And the change in temperature here, negative 73.4 degrees Celsius. So those negative signs cancel again. And to two significant figures, 0.40 joules per gram per degree Celsius. A little bit of error here, which is expected with these experiments, but we're really close to that 0.39. And based on the color for that cylinder, that looks a lot like copper. And here's the data for the last trial, that larger metal cylinder. 50.0 milliliters of water, we'll assume the 50.0 grams of water. Here's the specific heat of water. The final temperature of the mixture minus the initial temperature of water. In this case, this is 12.0 Celsius. A bigger change in temperature, but again, we're using a much larger piece of metal, so this is expected. This metal had a mass of 81.828, there's a negative sign in front, times the final temperature for the metal, and of course the initial temperature is right at 100 Celsius, so this delta is a negative 65.1 Celsius. So we'll answer to 3 sig figs. In this example, we get 0.471 to 3 sig figs. And it's a larger piece of metal. We do get some error here. So this looks a lot like stainless steel or iron. Just a word on the error. The metal pellets seem to get really close to the actual value for the specific heat. Again, I'm ignoring the calorimeter constant, which will not make a big difference, but we see that the smallest error is with the zinc, the metal pellets. Uh, I suspect because of the metal pellets, we have a larger surface area. We're able to heat up more of the actual metal, and that heat is transferred to the water. With the cylinders, of course, we're heating the cylinders, but the total mass, because it's a cylinder, sometimes that inside of the cylinder may not absorb the initial heat from the water, and thus that heat is not being transferred over, so that initial temperature may be a little bit questionable. Again, the smaller metal had a smaller error compared to the bigger metal, which had a little bit more error. So right around about a 5% error, which is generally acceptable.